and letter C. You have the paper? Oh, thank you. You have the papers in front of you. So discussion 1. We're looking at 2C. And 2C is like so. They want you to draw Lewis. Oh, I'm allergic to organic chemistry now. I think that's what's going on. Did everybody come up with that? That will be the structural formula. If they want to do Lewis, you really, really want to make sure that you add your lone pairs, right? So you want to add the lone pairs. Really, that will be Lewis structure, the structural, we don't care. In reality, they don't ask for anything else, okay? They don't ask for anything else. Okay, I'm going to do letter D, and in letter D is the SOCl2. This molecule is called thionyl chloride. My students have called it so cool, and so that's the only name I remember. They want S to be the central atom, and I'm going to draw like so. And I want to make sure that I put my lone pairs, and I know that it all begins like so. So I have, how many total number of electrons in this structure? Does anybody know?
26.
How many? 26. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Is this correct? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, I'm going to start out like this, okay? I want to start out like this, and when I start out like this, and this is just me telling you the evolution of Dr. Lewis coming up with formal charges. If you look at it like this, the chlorine has a formal charge of, what is the formal charge on chlorine right there?
0.
0. Is everybody agreeing on 0? Everybody agrees on 0. Everybody agrees on 0? Chlorine has 7 valence electrons, and you have 2, 4, 6, 7. So since I know chlorine has 0 and chlorine has 0, I don't bother writing it, right? I'm not bothering writing it. When I look at sulfur, sulfur actually supposedly has 6, right? Sulfur is in group 6. It has 6 valence electrons. And now it has how many that belong to it? Has 5. So there's a +1 formal charge on the sulfur. If I look at the oxygen starts out with 6, and now the oxygen has how many that belong to it? 7. So the charge on the oxygen is a -1. True good Lewis structures should have no formal charges on any of their atoms, okay? So can we fix it? Let's see. Would I be able to bring that pair of electrons and form a double bond here? Can I bring that pair of electrons here and form a double bond there? Yes or no?
Yes.
Why yes? I say I'm doing this. I'm going to draw with pencil.
No, you can't do
I
that.
said I'm bringing this guy here, and now the double bond is there. Can you do that?
No,
No. The answer is no. Why not?
there's no more room.
How many electrons around that oxygen now? There are 10 electrons around that oxygen. There is no place to put those 10 electrons. Oxygen lives on the second energy level, right? Oxygen is on the second energy level. If you live on the second energy level, all you have are the S and the P's. As generous as one might be, there are 2, there are 6, there's a total of 8. That's how that octet rule came to be. You give them to me, I can't. Kind of driving to Tahoe New Year's Eve, and you see no vacancy, no vacancy. You've got the money, you've got the time, no vacancy, no room. That's oxygen. You cannot do that. But you do this? Can you do this? Can I go ahead and bring a pair of electrons from the oxygen? What if I do that? Okay, if I do that, I'm gonna redraw this. When I redraw this, now it looks like so. I have a chlorine, a sulfur, a chlorine. I have a double bond O, dot, 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 and I have these dots now. What are the formal charges? What is the formal charge for oxygen now?
0.
Is everybody seeing 0 for oxygen? What are we seeing for sulfur? Is everybody seeing 0 for sulfur? Okay, this is how Lewis looked at it. Oh wait, how many electrons do you have around the sulfur? 2, 4, 6, 8, 10. Why can you? Sulfur is in the third energy level. Sulfur in the third energy level, you have the s orbitals, you have the p orbitals, and you have the d orbitals. They're there. They're the total opposite of what we saw with the oxygen. The orbitals are there. I don't need to use them, but if somebody gives me the extra electrons, I certainly can put them on that d sublevel, okay, or the d orbitals. You did do hybridizations in Chem 2 where you had the dsp3, the dsp2. This is going to be one of that categories, okay? So in organic chemistry, this is called expanding the octet. We don't really get into the hybridization of these guys. We call it expanding the octet. Anyone, well, atoms on the third energy level, so for us, atoms, OChem, this is the OChem world. Atoms that can exceed 8 electrons around them these are the typical ones that exceed the 8 electrons around them, are phosphorus, sulfur, and chlorine. So these guys are our most commonly atoms that will expand that octet. All right, we're moving to letter number 3. Oh, no, wait. So we do letter E, right? So now we've done. Is everybody okay? Now we're doing letter E. And letter E looks like this. They're saying that this is M2H2. This should be 5, 10, 12. There's a total of 12 electrons here, right? So the nitrogen to the nitrogen to the hydrogen like that. You put a double bond. We have 2, 4, 6, 8, 10, and 12. And that was that compound. Did everybody draw it like that? All right. We move on to number 3D. So the next one to do was 3D. And in 3D, on the discussion one, the molecule is C2H4O. And they want you to do 2 compounds. Already you see that there are 2 less hydrogens, right? There are 2 less hydrogens than the typical 2 carbons. Yes, everybody sees that? So I know I'm going to need to have a double bond. So obviously, I think the only way that I can do this is if I have a double bond to one oxygen. If I put a double bond to one oxygen, I have 4 hydrogens remaining. That will be 1, this is 2, this is 3, this is 4. This is called an aldehyde, reviewing your functional groups. 4, you should be able to have a carbon, doubly bonded to a carbon. That's called an unsaturated. Unsaturated is every time you have less hydrogens than you can. When I go ahead and I put an OH, I have a hydrogen, a hydrogen, a hydrogen. This guy would be called an unsaturated alcohol. This actually does not exist. This one would be called an ene for a carbon-carbon double bond. All for the alcohol. This is the last chapter in your Chem 4. So this will be the last chapter that we have to study. Right now, we just recognize them, all right? So right now, all we need to do is just recognize them. Okay, we're moving on to number 4. So we're done with that. We move on to number 4, and we're looking at this guy. I thought I had all this drawn, obviously I just don't. I don't know where they are. When I have this C2H2 whatever, and I'm hoping that people will help me out with a number of things. 4A, we have a CH2, an NH2, and that, right? So the total number of carbons, of hydrogens, electrons, holy Lord. How many electrons are here?
12.
They're telling me 12. So 12 electrons is the magic number. And you have to follow the connectivity. This says that there's a carbon that is bonded to a hydrogen and to a hydrogen. And I have a nitrogen that is bonded to a hydrogen and to a hydrogen. All right. And that takes care of 2, 4, 6, 8, 10. I'll give this guy the lone pair. I'll come over here and I'll do this. I'll give this guy the lone pairs. And the first thing that I say on an exam is there's something wrong with the structures. And the answer is, what is missing? What is missing in both of these structures? Formal charges. I cannot keep leading you, otherwise I answer the questions for you. So when somebody says what is missing in these pictures, obviously what is missing is a formal charges, all right? So formal charges, 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12, all right. So, is there a charges on here?
Yeah.
The carbon is a -1, the nitrogen is what? A +2. Over here, the carbon is a +1, the nitrogen is 0. This is structure number 1. Structure number 2. Which one's major, which one's minor? Between 1 and 2. 1 and 2, which one's major? 2 would be major. And 2 is major because less charge separation. Okay, that will be it. And the most electronegative atom has the extra electron, right? This will not even exist. So let's say you did not draw this, right? She says to draw 2 or 3. So I'm drawing 2 or 3. So obviously, and I think, Kyle, this is probably what you were going to say. Ooh, that's a nitrogen gone crazy. So I think the obvious answer is that that lone pair is going to move and form a pi bond, right? So maybe we have that. And now if we have to assign charges, the nitrogen is the +1. This guy became number 3, right? This guy became number 3, and now she says label them as major and minor. So that word does not exist. And then you start with your nice little paragraph, right? You start, let's say I give this to you, right? So I have put these 3 structures on your paper, me drawing, I put the 3 structures on your paper, and she says, of the 3 structures, which one is the major and why, right? Of the 3 structures, which one is the major and why? Then you should be able to bring in all the criteria and say, which one is the major? So structure number 3 is a major because you have a full octet for every single atom. You have as many bonds as possible. Take a look that in these other 2, you had 1, 2, 3, 4, 5. You had 1, 2, 3, 4, 5. And over here you have 1, 2, 3, 4, 5, 6. That's what they mean as many bonds as possible, all right? All atoms have a full octet, as many bonds as possible, and do not use that the most electronegative atom has this charge, because the most electronegative atom is the fission of the electron. So you would not use that in that category, okay? And these are really not true resonances, because it's not obvious how we're moving the electrons, right? The pushing the electrons here is not very clear. Everybody okay? Yes? The third one is the major, yeah. Number 3 would be the major. Yeah, the other ones are really not. The other ones is just play. The other one is just so that we have something to talk about, right? I don't know what I've done with these things. Woo! I'm so sorry. I come back. Did anybody come up with another drawing for this one? Sorry, I'm coming back. Forgive me, mea culpa, mea maxima culpa. Does anybody come up with another one? I certainly did after I'm done talking. What about a ring? Ooh, can I just not do this? I could have done that, right? I could have done that. And what functional group would this be?
Ether.
An ether, where you have your oxygen singly bonded to carbons. That's your ether. Okay. Yeah, I should have known that. Is everybody okay? All right, backing up. I already did B in class, so let's go ahead and do C here. So letter C, that looks like so.
That has more electrons.
The one before?
Yeah.
All we were trying to do here is coming up with that molecular formula, C2H4O. So I had C2H1234O, C2H1234O, C2H1234O.
So we would put the double electron.
I can put the lone pairs if you want. Yeah? I don't know what are we questioning? I'm not sure. Did you count the number of electrons in each? Is that what you guys did? So 2 times 4 is 8, and 4 is 12, and 6 is 18, right? So we needed to have 18 electrons total here? Is that what we're doing?
Yeah.
Okay, so then we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's 18 here. So there's 18 in this aldehyde. And we have 2, 4, 6, 8, 10, 12, 14, 16, 18 here. And we have 2, 4, 6, 8, 10, 12, 14, 16, 18 here. So there's 18, 18, 18. All right, obviously we didn't think about that, I just thought about it after all that. All right. So letter C looks like this. For letter C we have the CH2, CH2, CH, CH2 minus. And the total number of electrons here is how many? 18 again. All right, and we have to follow the connectivity, right? So we're following the connectivity. So this carbon is bonded to 1 and to 2 hydrogens, and is bonded to a carbon that is bonded to a hydrogen, and is bonded to a carbon that is bonded to a 1 and to a 2, like that, right? And that takes care of 2, 4, 6, 8, 10, 12, 14. So I can do 16 and I can do 18. Or I can do this. let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18. So let's say I have these two, right? Let's say I have these two. And this is what I give you. What's the first thing you're going to do? First thing you're going to do? Assign formal charges. Okay, first thing that one will do, first thing, assign formal charges. I am not going to tell you that, okay? I think if I tell you, you would do it. That's not the point. I think the point is, in order for you to come up with the delivery of your thought process, the first thing that you innately should do is take a look that this doesn't look right, okay? When I assign formal charges, this is a -1, this is a -1, and this is a +1. Is everybody seeing this is not going to exist at all? There's no way you're gonna have a minus and a minus. So could you have done a better job with this? Nothing else, but just change this around. What could you do to just fix this? Not another structure, just to fix that one. What would you do instead? No double bonds. What else could I do? Kyle did this structure. Okay, so Kyle had that structure. And then Amber, she did this structure. Okay, so that's Kyle. Now this is Amber. And I'm drawing all these things for you on a paper. This pen is going to go away and die. So that's this other student. And we put charges. This is a -1, this is a +1, this is a -1. Is Kyle's better than Amber's down here? This doesn't exist. Is everybody seeing the difference? Yes or no? Okay, one moment. You cannot make it a ring, there's too many hydrogens. Well, you cannot. Okay, 1 minute. Is there one better than the other? Is there one better than the other? The answer should be yes. Yes, 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 yes. You have to defend one or the other. Are you defending the top or the bottom? You better be defending the bottom, okay? Both of them are wrong, no doubt. Both of them are wrong. I'm not saying one is right or wrong. Both of them are wrong. This is not going to exist. There's no way you're going to have a negatively charged atom next to a negatively charged atom. In this one, you have a -1, a +1, a -1. This might exist, okay? This will not, okay? This will not. You're not going to have two electrons repelling one another, so this will not exist. Neither one of these probably should have been drawn. We're only drawing them because we want to play with this today, right? If you went ahead and you drew this one, and we have here a -1, okay? And I say draw resonance, these are what we call true resonance form. Finally, we got to a true resonance form. A true resonance forms, you are able to move electrons, push electrons from one side. Oh! Here we go again. Ignore all that. I do not like that at all. I'm going to come down here. That is major bad. Oh, I really did lose the pen. All right. So that was major bad. Did you see that? I don't know if you noticed what I did, but what I did was unacceptable. Unacceptable. Okay. This is your -1. Your arrows always begin from a region of high electron density to low. My arrows were going to be totally wrong, and I would have marked you wrong. Is everybody there? If this was your arrows like I was about to do, this would have been wrong. The region of high electron density is the atom that had that extra electron. Arrows go from that lone pair to form the pi bond the pi bond moves here. Okay? When I draw the other structure now looks like this, where you have the carbon, the double bond, like so. Everybody there? These are the ones that you put the brackets, you put the minus on the outside. These guys are really called true resonance form. Somebody would say they're exactly the same. That's exactly what they are. True resonance forms are identical. And you can move electrons back and forth and end up over there. Take a look that they all have a full octet. They have as many bonds as possible. The same atom carries the same charge, and you have the same number of charges on the atoms. Those are called true resonance form. This is what we're striving for the whole year, okay, for true resonance form. If you were to have like a mirror, right, if you take one structure to the mirror will see that. Okay, the mirror will see exactly that. Okay, any questions about this? Amber said, can I do a ring? The answer is, you cannot do a ring when they're giving you a condensed formula. Okay, the condensed formula, the connectivity is like that. You need to have a CH2 to a CH to a CH2. In a ring, we cannot make it in condensed formula. So if this is my ring, sorry, that is it. There's no condensed formulas for ring. The ring is it. You have a molecular formula and you have the ring. We cannot untie it to put it into a condensed formula. So this will be your C2H6. That's the only thing I can do with the ring, okay? I cannot open it up and make it be like a straight chain thing. Okay, letter D. We're going to letter D, and this is 4D. And 4D looks like so. I have an HO, a CH, an NH2, and over here is a plus. And how many electrons here again? Anybody counted? 18 again. So I'll start from the left, and I put an H, O, C, H, N, H, H, and they 118. So I do 2, 4, 2, 4, 6, 8, 10, 12, 14, 16, 18. That's one structure. Or I'll do this. And there are many permutations of this, and I don't want to waste all that time. So these are the only two I'm going to draw so that you can defend them. Okay, so if you have to defend these two, if you're defending these two, the one on the left and the one on the right, first thing you're going to do is you're going to go ahead and add formal charges. When you add your formal charges, oxygen is 0, carbon is a -1, and nitrogen is a +2. When I come over here, the oxygen is a 0, nitrogen is a 0, this one is the +1. Obviously, left or right, which one is the most acceptable of the structures? Right for you guys? Right for you guys is the most acceptable, right? Right? I don't think that's gonna work. I don't think that's gonna work. Right? You have the carbon with a -1, so carbon is rich. Nitrogen, the more electronegative, is deficient of 2. Not going to happen. If this is what I give you to defend on an exam, you very quickly say, structure on your right is going to be the major, and you already know why. Okay, yes, I don't have a full octet, but I am the more electronegative, and I have the electrons that I have in my common bonding patterns. Is there a best resonant form? Is there the best? Yeah, the best will be what? Coming here, and recognizing that you can actually have the nitrogen with a double bond. When the nitrogen goes in with a double bond, the nitrogen now is a plus, which is really hard because I just finished saying that the most electronegative have that. But remember, the big criteria at the very top of it all is that every atom has a full octet. That's overwhelmingly the highest criteria. And in this picture, every atom has a full octet. So this is by far the major resonance contributor, okay? Everybody okay? Alrighty, let's go ahead and put, yes? Go ahead.
Is it possible to have a double bond between the oxygen and the carbon?
Is it possible to have a double bond between the oxygen and the carbon? Well, it is possible. It is possible. But in reality, so she says to do this. She's telling me to go ahead and do this. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So she says to do that. Right? She's saying to do that, and then obviously it's obvious that the oxygen is a plus 1 now. So that is possible. That is possible. And I could probably say that if I had given you these three only, so let's say these are the 3 that I give you, which one will be the major of these 3? Let's give them numbers so that we can, let's go ahead and give them numbers so that we can talk with numbers. So this is your test, your quiz, and these are the structures, 1, 2, and 3. And I say, which one will be the major?
2.
People are saying 2. They're saying 2 is, this is 2 now. They're saying 2 is the major. Okay, I guess we can say that I hope no one says 1 is the major. Okay? So we're going to take 1 out of the picture. No one picks 1. Everybody? No one picks 1. So 1 is really not the option. 1 is gone. So now it's between 2 and 3. How many people say 2? Raise your hand. Okay, how many people say 3? Raise your hand. I'm going to say 3. Why are you saying 2? This is 2.
Because it has full octet for each. And it has full bond.
But I guess oxygen's more electronegative, so we wouldn't have a positive.
Oh, okay, wait. Do we have 18? 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Ah, I see what people are saying that number 2. So people pick number 2 based on that. You know what? You know what? If we're following the rules, right? If we're following the rules, guess what? We will have to pick 2. Everybody, if you're following the rules, we would have to pick 2. Because in 2, everybody has a full octet. In 3, the carbon does not. And not only that, you have as many bonds as possible, right? So in here you have your 1, 2, 3, 4, 5, 6, 7. Here you have 1, 2, 3, 4, 5, 6, right? Sadly, I have to say that, yeah, this will be the major based on that criteria. I can tell you that oxygen seldom does that. But all you have is the criteria to defend your structure. And if you're using that criteria to defend that structure, then that will be the major. It's everybody. That's scary, but it's true. That is scary, but it's true. It's everybody. Remember that you don't want to create new stories. You know, people really are very creative on exams. All you want to use is what you were given. It's the more stable. Okay, based on what? So what was given, if you follow what was given, your major will be that. Oh, I can't even stand it. All right. I Oxygen seldom does that, by the way. Oxygen never does that. Yeah?
So is there a difference between that one and the double bond with the nitrogen?
This is the best.
Okay.
That is the best. So in reality, we just were defending these two, but in reality, this is the correct Lewis structure. It's everybody. If you're comparing now this one and this one, so the comparison really should be between 2 and 4. Okay, between 2 and 4, 4 should be the true Lewis structure. If in your other class they ask you to draw Lewis structure, this is it. This is the correct Lewis structure. Everybody, all we have done is play. Organic chemists like to play. That will be the correct. Okay, so. All right, for this one, they want you to determine the formal charge. I went ahead and I think I've drawn a lot. I don't know if you've drawn. All right, let me just go ahead and draw. So they have it showing like this. We're moving to 5A. We're moving to 5A, and in 5A they have this like so. CH3, 2O, BF3, like this. And so I'm going to have that oxygen, and I'm really just going to draw the CH3s like this, because I'm not interested in them. And I'm going to have the B with the Fs like that. And I'm really not going to put all the lone pairs anywhere else, but the oxygen here is going to be a +1, and the boron here is going to be a -1. Yes? Did everybody come up with a +1 and a -1? Okay, oxygen started out like this. Oxygen started out like this with a dot dot and a dot dot and a CH3 and a CH3, and this is bent. And boron really started out like this. Like so. I think in your Chem 1 or Chem 2, the boron always was trigonal planar. In our class, if you can donate a pair of electrons, okay, you are said to be a nucleophile. So I am a nucleophile. A nucleophile is an electron pair donor. I am also called a Lewis base. So you need to know all of this. These are the last of the words of chapter 1. So this is all wording from chapter 1 that we did not cover. We're including them in here now. If I am an electron pair acceptor, I am called an electrophile. Electrophile, the word makes sense. I am a lover of electrons. I am an electron pair acceptor. Okay, my electron pair acceptor is then called a Lewis acid. Okay, so Lewis acid, take a look that now, I mean you did, and I want to finish chapter 2. Chapter 1, chapter 1. There are 3 theories of acid base. 3 theories of acid base. The simplest theory of acid base was the Arrhenius. Does anybody remember what Arrhenius said? How did he describe a Lewis acid? A Lewis acid is a compound that will go ahead and donate H pluses in solution of water, in water, make a solution. So a Lewis acid, you have to have something like that. So it makes it It kind of was very limited. It was very limited, so for you to be an acid according to Arrhenius, so Arrhenius, okay, Arrhenius said to be an acid, you actually had to be this. So you had to have hydrogens in your structure, because when you went ahead and you threw that into a beaker of water, you had to produce H pluses. So he defined an acid as a substance that produced H pluses in water. Very limited. HCl, HNO3, H2SO4, HClO3, you needed to have an H. If you didn't have an H, you could not be an acid. And he described his base as a substance, so he described the base as a substance that will go ahead and make or produce, this one of course dissociates, this one is ionizing, OH minus. So you needed to form OH minus in the beaker of water. Put it in water, you dissolve, you have OH. Very limited again, very limited again. Because if the structure did not have OH, you didn't have a base. He didn't live too long in his theory of acid bases. Very quickly, people by the name of Bronsted-Lowry came into the mix, right? Bronsted-Lowry, gone from the picture. Bronsted-Lowry said what? In your Bronsted-Lowry, what happened here? Bronsted-Lowry. How did he define an acid? He defined an acid as a substance that donates a proton. So he donated a proton, donates proton. Well, guess what again? You kind of need to have hydrogen in your structure, right? So things that donated protons, we're going to go ahead again and call that. But that was too strong of an acid, so he did not play. I don't know if you remember that. That only weak acids kind of play the story in the Bronsted-Lowry. So I'm going to take that guy away for now, okay? And I'm going to bring you my acid. My typical story about my acid is this one. I think I've introduced them to you. My carboxylic acid. You know this guy by many different ways. I think in your other course, maybe they drew this one, I don't know, possibly like this. I'm erasing. You may have seen this possibly like this. I insisted that your teachers drew it like this, opposite to a Chem 10. I have no power over those people that may have drawn it like this. So all of this means the same. I don't know if you've seen acetic acid drawn like that. Have you seen acetic acid drawn like that? Have you seen acetic acid drawn like that? Okay. Okay, we like acetic acid drawn like that. Okay, this is like a Chem 160, Chem 10, where you go ahead and you always started an acid with a hydrogen, helping the students to know that these guys are non-polar and they will not be able to ionize. Carbon-hydrogen bonds are non-polar bonds. We cannot break them. There's not enough energy in this world. Well, that's not true. Sorry. We get to chapter 4 and we're going to be breaking them. But in water, it's not going to happen. How's that? In water, it's not going to happen. So we're going to take this away. So your acid will go ahead and donate the proton. Okay. Which proton? The most acidic. This is the most acidic. These guys are not acidic at all. Okay. And the base did what? The base accepted the proton, right? So the base accepts the proton. Well, we get here now to my Lewis, and there are no hydrogens in the mix. So everybody, we get to the Lewis, and there are no hydrogens to the mix. So that's why Lewis came to be. There was yet another way of looking at things. So Lewis described them then as electron pair donors or electron pair acceptors. Okay, all of this is chapter 1, not 2. All right, let's take a look at letter B. And in letter B, this looks like so. I have a C, letter B. I have a C. hydrogen, and a hydrogen, and a nitrogen, and a double bond nitrogen, and we have dot dot and dot dot, and all we wanna do is put charges, and the charges are what? Well, the carbon is a +1, the nitrogen is a 0, and this guy is a -1, yeah?
Yeah.
We do letter C, and letter C is a carbon that has hydrogen, hydrogen, double bond to a nitrogen, double bond to a nitrogen, dot dot, dot dot. That nitrogen is a +1, this nitrogen is a -1 and also good, yeah? We get to letter D, and letter D looks like this. There's an oxygen to an oxygen to an oxygen, and there's a dot dot, dot dot, dot dot, and there's a dot dot and a dot dot. Is this correct? I don't think so. Oxygen is in group 6, so I should have 18, yeah? And I have 2, 4, 6, 8, 10, 12, 14, 16. She's missing a pair. She's missing a pair. It was impossible to draw it. Impossible. I tried, and then I quit. All right, I tried, and then I quit. So there's that. So if we put that there, what are the charges? If we put that there, what are the charges? -1, a +1, and a 0. This is really O3, this is ozone. You've heard of the ozone layer? Can you do a resonance form? Yes, you can. And these are also called true resonance forms. Okay, these guys are also called true resonance forms. Would you be able to draw the arrows to represent them? The answer is yes. You do not want to make a mistake like I did before. You want to make sure that you move them correctly, right? You want to make sure that you move them correctly. And so I have that oxygen, like that, dot dot, dot dot, dot dot, dot dot, dot dot, dot dot. You don't have to draw the dots, by the way. If you want, you can just put the lines to go faster. Somehow, when you're doing resonance forms, it doesn't look too good. As we get through the course, you can use the lines, call it a day. All right, and then the very last one in this mix, which is letter E. And letter E, I have this carbon that is bonded to the phosphorus. They say I have a hydrogen and a dot dot. Obviously, that's a -1. And then the phosphorus has a CH3, a CH3, a CH3, and then the phosphorus is a +1. All right, we're done? Not quite. We have the back side of this. In the back side of this, they want you to identify the acid and the base, la 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 la, assign. So, let's take a look. If I have, so this is 6A, and they want you to draw the Lewis acid. So I'm gonna draw it like so, right? I'm gonna go ahead and put them like this. That's my first structure, everybody. That's the first structure. This is actually an ether. And then somehow, some way, magically, an H+ arrived. Who brought the H+? We really frankly don't care. Is everybody there? We really frankly don't care who brought the hydrogen along. That is not what we're trying to do right now. Even my molecular orbitals have died here. So the oxygen now is a +1. The question is, who was the acid, who was the base? So what was the role of this one? This one was the base according to Bronsted-Lowry, accepted the proton, right? base, accepted the proton. Bronsted-Lowry in blue, I was the base, I accepted the proton. On the return, I would be the acid, right? On the return, I was the acid, I went ahead and I gave the hydrogen away, okay? Bronsted-Lowry in blue. Lewis in red, what was the ether? Lewis, what was the ether? Lewis was the base, this was Lewis. It was a Lewis base because it did what? It donated the pair of electrons. Okay, so I was the base. And who was the acid according to Lewis? I was the acid, right? According to Lewis, Lewis acid is this guy that accepted that lone pair. Okay, so back again. In the case of Bronsted-Lowry, I'm the base because I'm going to accept the proton, right? Somebody's going to give it to you. It's coming from the water most of the time, okay? So if I'm going to go ahead and take the proton, I'm going to be the Bronsted base, accepts the proton. On the reverse, I'm going to be the acid. I'm going to donate it back, okay? Yes?
So for the test, do we have to know both the Bronsted and Lowry?
You have to know them all, yeah. You have to know Bronsted-Lowry, you gotta know Lewis acid and base, yes. Okay, is everybody okay? I think the question here was really mostly not even that. What they wanted you to do was take a look at the structures, like for letter B, that looks like this. All I wanted you to do was to be able to draw. So everybody, I wanted you to be able to draw. So in the case of the H2CO, the only way that this works is like that. That's that. And the H2CO is like that. So of course we need to put my lone pairs here. So who's deficient of the electrons? Can you see who's deficient of the electron? It's the oxygen that now is the plus up here. Okay? And so we call this the base, according to Bronsted. I'm going to accept the proton. We accepted the proton. If you're going that way, I was the base. If you're coming this way, I'm going to be the conjugate acid, right? The acid donates the proton. Is everybody okay? Yeah? All right, let's take a look at letter C. And letter C, we write it like so. And the other one is like this. Again, they wanted you to draw. So they want you to draw. We're drawing. So that oxygen has one hydrogen, two hydrogens, and the CH3. And then over here, this one has the oxygen with a hydrogen, with a CH3, and the two lone pairs. So it is the oxygen here that has the +1 charge. If these were double-headed arrows, like that, I am going to be the acid, right? Can you see that I'm going to be the acid? I'm going to donate the proton, and you're going to be the base. You're going to accept it. Okay? Bronsted-Lowry. Everybody okay? All right. Number 7, they want you to actually draw. Okay, number 7, they actually want you to draw. I'm going to go ahead and use my line angles. So my nitrogen is going to look like this. doesn't look anything like what you have here. Is everybody there? That's number 7. It says, give the structural or condensed formula of the conjugate acid. There's no way I can do this. They want you to show the conjugate acid. So if I am the base, and you want to draw the conjugate acid, the conjugate acid would look what? I'm the base.
Donate.
I'm going to accept it right there, right? So you're gonna look like this now. I accepted that acid, and I'm like the plus, right? But she said, write structural formula. Okay, that's my structural formula without the CH2, CH3s. Yes, can I do that? Condense, I don't know. I leave it up to you guys. Maybe somebody put condense like this. This is probably how I would type this, by the way. It would be the easiest way for me to type that. That looks to be like condensed. Otherwise, I don't think it shows any better.
So if it has any positive or negative charges, do not lead to the acid.
Okay, letter B. I'm gonna go ahead and use my line angles. They work so much better. Wait, I had 1, 2, 3. Can I draw it like that? I think it works really so much better. There are some people that I actually don't remember them still very well. One of them is Ashley. You are Ashley. Jeanette, Nicole, Roselle. I don't think Roselle is here today. Roselle, are you here? I didn't think so. Okay. That's what I thought. Okay. Christine, Arian, Dean, Israel, Kyle, Jason, Michelle, Laura, Jasmine, Nick, Mark, Amber, Melanie, Sam, Christian, Alex, Kylie, yep, Simra,
They just call me Sid.
Sim. Okay. Thanks. Jessica Troth. You're Jessica. Leanne Umali.
Here.
Where are you? I know. I'm like, Kevin and Eunice. So who did I not? Eunice, you're not here either? You're Eunice, okay. All right.
I have a question. On your formula for the acid on A, shouldn't there be there's 2?
Yes, there is 2. Thank you. There is 2. There are 2 there. So sorry. All right, so now we put it with the acid, and with the acid I will have that. And I'll put a hydrogen there and a dot, and that's the plus, right? So let's put that acid red or some other color. That will be it. I think this one, again, for the condensed formula, somebody might go ahead and put this as CH3, CH2, CH2. You'll have that as an S. Parentheses, this doesn't work very well. Is everybody there? And a hydrogen is. So a lot of these things, people do not use condensed formulas, okay? They're not working very well. That doesn't even look right for me. So, I don't think you will be asked to do condensed, because that doesn't look right at all, everybody. So if you drew this, okay, this is as good as it's gonna get. Oftentimes, possibly the better drawing, this looks bad, the better drawing would have been this. And then the plus, and it still doesn't look right, it's everybody. So you can go ahead and do it as in structural formula, I'm okay with that. Okay, the very last one is gonna be even worse. When you have double bonds, there's no condensed for double bonds. So back again, I'm gonna draw it like so. That is that. In the line angle drawing, the line angle drawing looks like that. As an acid, it's gonna look like this, where you tie this to the hydrogen, the oxygen is a plus, and you only have one dot dot. Not good in condensed. This one in condensed works. This one in condensed may work. Some people would have typed this like so. They would have gone CH3, CH2, CO, CH2, CH3. That might work. This does not work at all. Everybody, condensed for this, nobody will get what you're trying to do. Because it might look like an aldehyde, which is not possible here. Okay, so there will be no condensed for that one. Okay, the molecular and empirical formulas, I hope somebody calculated that. I think I calculated, I finally, at the end of almost lecture, I figured it out. So, they're asking for adenine, so this is what I did. Oh gosh. So they gave me, all right, it just doesn't work. This is why I'm not a PowerPoint person. So they're telling you two things. There's only two bits of information that you have. They're telling you that the empirical formula, right, so they're saying that the empirical formula, I'll do the first so that you know how we want this done. So the empirical formula is CHN. So I go ahead and I calculate the molar mass. So you want to calculate the molar mass. When you're calculating the molar mass, there's one carbon, one hydrogen, one nitrogen. The one carbon is 12.01. The hydrogen is 1.01. The one nitrogen is 14.01. After you add all of this, this is 27.03. That's the only thing I have so far. But they're also telling you that the molecular weight, so they're saying the molecular weight over here, given in the problem, is 135, and that was given. So there is something out there that says, if you put the molecular formula mass over the empirical formula mass, you're going to end up getting a number. And that number will either help you come up with the molecular or the empirical. So my molecular weight, that is 135 given in the problem, divided by the 27.03 that I just calculated out, this is giving me a number 5. And number 5 is that number that multiplied by each, right? So you have this 5 over here. That 5 times your 1, your 1, and your 1, you end up with a C5H5N5. And take a look. If you multiply the moles of the empirical formula times that number, you come up with the molecular formula. If you take the molecular formula and you divide it by that number, you come up with the empirical formula. And that's as hard as this is going to get for us. No harder than this. This is all that is getting for us. So I did 8A. Did everybody do them all or no? Yeah? Yes or no? So I did 8B, and that little round was 10. For letter B, so for my B, that round that I'm calling here was a number 10. What do you call that number? That I'm going to either use to multiply it or to divide to get from the empirical to the molecular. the number. Don't know what you call it. So it's C3H5. This is the empirical formula. The empirical times the number. You end up with the molecular. The molecular divided by the number, you get the empirical. Is everybody, I don't know, factor. Factor. Multiplier, but it can be a divider. Factor. We're done. We got a new title for it. Factor. No idea what it's called. All right, and then letter C. What happened with letter C? What is that? What is that round number there? I came up with 8. For my factor was 8 for this one, and so the formula was C3H7. The empirical, the molecular was then C40H56. Everybody okay?
40.
Number 9. Oh, I'm gonna show number 9. I have no patience to draw. We're running out of time. So number 9 looked like that. That will be somehow the structural. Take a look that is really not totally the structural. Because the structural, they want you to put all the lines. Like I have no patience. This is going to be my structural. I have no patience. Okay? Yes, that will be okay in the test, unless the structure is small and I say strictly structural. Otherwise, I mean, takes too much time. It takes too much time. And that's not even structural, right? Is everybody agreeing that structural will be carbon line, 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 impossible for that one. All right. Same thing is true for letter B. Impossible. I cannot put all those lines. I don't have the patience. You have it. I don't have it. That's mine. Because that's really structural. Like that. Oh, I can't do it. I cannot do it. So you can have all your lines if you want. And my letter C is that one. And again, see how I destroy all this? Oh, no. Did you do it like this, or you actually did all your nice little lines?
Well, no, I kind of use my like the
You did a mixture of both. That one actually doesn't have a title. This is a hybrid. We're going to call it a hybrid of structural and condensed. How's that?
Okay.
I don't think it's got a real name to it. It's called getting lazy quick. That's what I'm going to call mine. The aldehydes, if you look online, because I know people love to search online, as if we didn't have enough to do. The aldehyde has the CH. They show it like that. Sometimes they draw it like this. So remember, if you leave it with a line, that's a ketone. If you leave it with a line, that's a ketone. It's got to be like that or with a hydrogen. If you put a line, it's got to be with a hydrogen. Okay, the very last one, so that I feel I've given it my all. Did anybody calculate that? How many carbons? I lost my paper already. How many carbons and hydrogens and stuff are here?
18 carbons.
How many?
27.
She says 27. Everybody agree with 27? I don't know. I don't have notes. I don't have notes. All right, let's use pencil here.
I got 18 carbons.
I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons. There are 18 carbons. Okay, after that comes the hydrogen. How many hydrogens? 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 3 is 27. Yeah? 1 nitrogen, 2 O's. Oh, no, we're done. Yes! There's 3 O's, she says. Oh, sheesh. All right, there's 3. Oh, so not good. All right, so let me tell you where we are so that we have an idea how life is. I have not moved on mastering to who has enrolled. Has everybody been able to purchase mastering, more or less?